Hello, everyone. We are Group 32, and this is our senior design that we work with YRC.
Hello, everybody. My name is Roxanna Ariza, and I am a senior in industrial engineering.
My name is Ricardo Donoso, and I'm a senior industrial engineer.
My name is Julia, and I'm also a senior in industrial engineering.
My name is Patryk Stalmach, and I'm also a senior in industrial engineering.
My name is Anthony Vuolo, and I'm also a senior in industrial engineering.
A little bit of background on YRC. YRC Freight is a leading company with less than truck loads, meaning they work with loads that are not full. Since 1924, recently they also merged with a few international companies in Redaway, Holland, and New Penn to create YRC worldwide. The problem statement we are focusing on is how to successfully allocate the amount of equipment needed for each shift. We are going to be focusing on a couple of locations, specifically 3 DCs or distribution centers, 309, 324, and 422, as well as 2 end of the lines, 303 and 318. We're looking to move forklifts, drivers, trucks, and trailers for city deliveries. So recently we incurred some problems in the problem statement. We can't focus on the cost as the data was not readily available. We were unable to study long distance deliveries or railways, and we had to condense the amount of locations to just those 5.
So in order to calculate the number of equipment needed to accomplish set goals, we came up with 2 different methods to do so. So the first method involves inputting bills per driver, the goals, and the total bills. And the second method involves inputting the number of drivers, the goal, and the hours per driver. And the company can use either method depending on what information that they have available.
We use R and RStudio for all the data sorting and handling. We chose R for its flexibility to analyze big data sets. YRC provided 2 weeks of data, all of it through Excel files. As stated before by Patryk, we just focused into 5 locations, 3 distribution centers, and 2 end of the lines. A big part of the time for this project was invested in data wrangling, which is sorting, merging, and mapping the data sets into something that we could work with. 3 data sets were provided. The first one was the city delivery, where we could find information like drivers, tractor, trailers used. From there, we calculated the essentials like production rate, which is bill per hour, and miles per driver. The second data set was Chronos, which is the timestamp for all the employees. This was separated into 2 DCs, into the DCs and the end of the lines. DC runs 3 working shifts per day and night, and the end of the line just do 1 shift. The third data set was DOG, that contained forklift drivers and the total amount of bill they move. So from there, we calculated the production rate. It is good to remark that the items shown on the bottom level of this diagram, they're all different in each location. Next, we used a constant workforce plan that we learned from our production planning class, where basically we treated the bills as demand, and then we divided it by their production rate. We wanted to find the minimum number of workers needed to complete the demand. Using this formula, we found out the number of workers. In this case, drivers needed. From there, we estimated the number of equipment based on the 2-week data provided. Here's an example of the required drivers needed for one of the DCs. Then, we follow the same method to find the optimal number of forklifts. Only this time, because DC worked 24 hours, we have to divide the DC into 3 working shifts. From there, we calculated the optimal value of drivers needed per shift and selected the biggest one in order to find the right number of forklifts that will successfully complete the demand. Finally, we summarize some recommended values for each location that allow us to explore some best or worst case scenarios. Also, in the case that we wanted to look into similar locations in the user interface, we have an idea of what are the limits of production.
So one big part of this project was the user interface, which we created in Excel. So right here, the cell selected is our user interface. We created a drop-down menu for selections. The things that have to be inputted are highlighted in this blue color right here, and everything else is a non-moving function, so that they should not have any input. They're only output variables. So the first thing you have to do in this in this interface is select which location your new distribution center and the line is going to be related to. So you can pick any one of these, and as you pick these different values, all the other values change throughout the rest of the interface. So if we wanted to change to 303, the rest of these values change. The next we have to change is the method. So you can select either method 1 or method 2 to find your outputs. As you select that, we also have, like Ricardo just said, the limitations. We got these from the data saying that, for an example, for 303, there could be no less than 8.21 or greater than 10.88 bills per driver. And this production rate changes for each of the facilities. So if we change this to 309, that number changes as well, because each facility has a different production rate. Same thing with the goals and the amount of drivers. Obviously, some facilities are going to be bigger than others, so they're going to have more drivers. Some can achieve a higher goal, and others can't. The next part of it is doing your inputs. So your inputs will change as if you select methods. So select method 1, you have to input bills per driver, goal, and total bills. Method 2, your inputs are drivers, goal, and hours per driver. So your inputs right here to the next cell over, it'll tell you if you're not in range or not. So how our bills per driver right here is above the maximum, it's not in range and will not calculate. So if I change that to just 8, it'll calculate. The same thing with the goal. The goal is too high for this location. I have to put it between these two requirements. I change it to 0.7, and it all calculates right there. And this is only for city deliveries, which you have to be remembered for, which is why forklifts are calculated in a different function, in a different way. So the same thing with forklifts as the other limitations that we have. We do have the minimum and maximum based off the data that we got. For each location, they'll still have a different bills per driver and total bills. Now keep in mind that this bills per driver and total bills is different than the ones from up here. They're different in the fact because they also take into consideration of all the bills going to the facility, while the previous one only took in consideration of the bills going to just the city, not anywhere else, not to different ends of the line. So with these two inputs here highlighted in blue, you can change that around as long as they're within the two ranges, and you will get a relationship between number of drivers and number of forklifts that will be needed.
As far as financials go, YRC financials are private, therefore they are not included in our project.
Some of the difficulties we found initially were gathering the data, the fact that bill weight and distribution centers do not have static working shifts. So in conclusion, using method 1 with the inputs of goals, bills per driver, total bills, and using method 2 with the inputs of drivers, goal, and hours per driver, we successfully found an optimal amount of drivers, tractors, trailers, routes, miles, weight, total bills, total paid hours, goals, and bills per driver. We also found that the number of bills per driver and total amount of bills can give us the optimal amount of forklifts needed. So some acknowledgements can be from YRC, Helda Fragoso, the senior engineer, Carlos Pichardo, operations service quality engineer, and Bob Shockley, the engineering director, and from UIC, Dr. Michael Brown and Dr. Quentin Williams.